But speaking about this
Yeah.
this walk along the path of innovation towards the dumb things being smarter than humans, you are now
Uh,
the CTO of Tenstorrent
uh-huh.
as of 2 months ago. They build hardware for deep learning.
Uh-huh.
How do you build scalable and efficient deep learning? This is such a fascinating space.
Yeah. So it's interesting. So up until recently, I thought there was two kinds of computers. There are serial computers that run like C programs, and then there's parallel computers. So the way I think about it is, parallel computers, you have given parallelism. Like GPUs are great because you have a million pixels,
Mm-hmm.
and modern GPUs run a program on every pixel. They call it a shader program, right? So, or like finite element analysis. You build something, you make this into little tiny chunks. You give each chunk to a computer, so you're given all these chunks. You have parallelism like that.
Mm-hmm.
But most C programs, you write this linear narrative, and you have to make it go fast. To make it go fast, you predict all the branches, all the data fetches, and you run that more in parallel, but that's found parallelism. Um, AI is, I'm still trying to decide how fundamental this is. It's a given parallelism problem,
Mm-hmm.
but the way people describe the neural networks and then how they write them in PyTorch, it makes graphs.
Yeah, that might be fundamentally different than the GPU kind of
Parallelism, yeah, it might be because when you run the GPU program on all the pixels, you're running, it depends. This group of pixels, say it's background blue, and it runs a really simple program. This pixel is, some patch of your face, so you have some really interesting shader program to give you the impression of translucency. But the pixels themselves don't talk to each other. There's no graph, right? So you do the image, and then you do the next image, and you do the next image, and you run 8 million pixels, 8 million programs every time. And modern GPUs have like 6,000 thread engines in them. So, to get 8 million pixels, each one runs a program on, 10 or 20 pixels. And that's how they work, but there's no graph.
But you think graph might be a new way to think about hardware?
So Raja Kaduri and I have been having this good conversation about given versus found parallelism. And then the kind of walk, as we got more transistors, like, computers way back when did stuff on scalar data. Then we did it on vector data, famous vector machines. Now we're making computers that operate on matrices, right? And then the category we said that was next was spatial. Like imagine you have so much data that you want to do the compute on this data. And then when it's done, it says, send the result to this pile of data, run some software on that.
Mm-hmm.
And it's better to think about it spatially than to move all the data to a central processor and do all the work.
So spatially, you mean moving in the space of data as opposed to moving the data?
Yeah, you have a petabyte data space spread across some huge array of computers. And when you do a computation somewhere, you send the result of that computation or maybe a pointer to the next program to some other piece of data and do it. But I think that a better word might be graph. And all the AI neural networks are graphs. Do some computation, send the result here, do another computation, do a data transformation, do a merging, do a pooling, do another computation.
Is it possible to compress and say how we make this thing efficient, this whole process efficient, this different?
So first, the fundamental elements in the graphs are things like matrix multiplies, convolutions, data manipulations, and data movements.
Yeah.
So GPUs emulate those things with their little singles, basically running a single-threaded program.
Yeah.
And then there's NVIDIA calls it a warp, where they group a bunch of programs that are similar together. Mm-hmm. So for efficiency and instruction use. And then at a higher level, you take this graph and you say this part of the graph is a matrix multiplier, which runs on these 32 threads. But the model at the bottom was built for running programs on pixels, not executing graphs.
So it's emulation, ultimately.
Yes.
So is it possible to build something that natively runs graphs?
Yes. So that's what Tenstorrent did. So
where are we on that? How, like in the history of that effort, are we in the early days?
Yeah, I think so. Tenstorrent started by a friend of mine, Labija Bajek, and I was his first investor. So I've been, kind of following him and talking to him about it for years. And in the fall, when I was considering things to do, I decided, we held a conference last year with a friend organized it, and we wanted to bring in thinkers, and two of the people were Andre Karpathy and Chris Latner. And Andre gave this talk. It's on YouTube called Software 2.0, which I think is great. Which is we went from programmed computers where you write programs to data program computers. Like the future is, of software is data programs, the networks. And I think that's true. And then Chris has been he worked on LLVM, the low level virtual machine, which became the intermediate representation for all compilers. And now he's working on another project called MLIR, which is mid level intermediate representation, which is essentially under the graph about how do you represent that kind of computation and then coordinate large numbers of potentially heterogeneous computers. And I would say technically tens torrents, two pillars of those two ideas, software 2.0 and mid-level representation, but it's in service of executing graph programs. The hardware is designed to do that.
So it's including the hardware piece.
Yeah. And then the other cool thing is, for a relatively small amount of money, they did a test chip and 2 production chips. So it's like a super effective team. And unlike some AI startups where if you don't build the hardware to run the software that they really want to do, then you have to fix it by writing lots more software. So the hardware naturally does matrix multiply, convolution, the data manipulations, and the data movement between processing elements that you can see in the graph, which I think is all pretty clever, and that's what I'm working on now.